Well, how are you doing? This video is going to be titled Angular Free Space. So, Angular Free Space. Um, I will be using some older stills from one of Randy's observations. This is something I annotated some time back, so this is not part of this. The writing isn't, and this arrow and stuff. Well, it is, but it is part of it. But it's not there. It's not something I annotated just before the video. And this is not about Ranty either. I'm just using some of his stills and other people's stuff and my own stuff for this. Okay, just so you know, there's this boat here out on the horizon. This is a big boat. This is a ship from his one for the observation video to Barrow Town Hall, which would be 18 miles away. This is a big ship. There is a small boat in it too, and you don't see that here. You only see it when he zooms in. So the angular resolution of the small boat, the angular resolution meant that the small boat just can't be seen. So all we're seeing is the big boat here, whatever we can see of the Barrow in the background. Barrow is over here. So, but I'm using this photograph for a reason, because I want you to be able to see the actual distance to Barrow and what it actually looks like. That will come in as part of it later. So, I just want to show here. This blue line is the surface of water or earth. The purple line is the observer's eye line, right? So let's just say Randy at the time, or anyone, right, when they're looking across water, their eye line is making a direct horizontal parallel with the water or earth underneath them. So they have this white area here between the two lines is the angular free space. So what happens is this angular free space and anything that's within it, anything that's within the view of it, will shrink with distance, let's just say, right? So the eye line, right, will appear to rise and will appear to drop. Like, so if there was something at a distance, it will appear, the eye line will appear higher than it is when that thing is close to it, basically, right? So if a car is close, from one foot observation height, you'd be looking at the tire. But when the car drives away across a straight, or a boat moves away across a straight, in a straight path, then you'll end up looking at up at the windows of the car and over it eventually, right? And the same with buildings. Buildings get smaller with distance. So the bottom, whatever is here now, I know it's slightly different across water, but whatever is at the surface, right? So at a building here, right? If a building was, let's say, this height up here, as it moves away to the observer from in perspective view, this is orthographic view, it'll appear to end up down here. So I'll explain it a bit more in a while. But basically, this is the point. These two lines never actually meet. They only appear to meet due to the angular size change of the free space. Okay. So this is from Ranty's 1 foot observation. This is a zoomed in version, a zoomed in portion of it. This is Barrow Town Hall over here, and this is 18 miles away, and this shoreline here is 13 miles away. I think that's 5 miles behind the shoreline. This is about center lens, and this is down at the water's edge. This yellow, there is superior mirage in this photograph. So this all up here is a mirage. So everything below the yellow line is the actual height of the buildings, and everything above it is mirage. Just for this part here, this is superior mirage. So there's a crane here that looks double the height. All these two buildings here look more high than they are, maybe double the height almost, or whatever. But just so you know, for later on, this is the actual height here. But that's not what I'm showing with this portion of the video. What I'm going to show is that from his position here, let's just say if this is just him looking across, that he's that close to the town, right? He's not 18 miles away, he's a bit closer. So if he was, right, this would be, let's say this is his eye line. As he moves closer to Barrow from here, if he moves in a straight line, holding a 1 foot observation, going across the water, his center center eye line will begin to drop down further and further further, because Barrow will be getting closer and bigger and bigger and bigger, and eventually he will be down here. That's where his 1 foot oil line will be, down there. Right when he gets there, right over to Barrow, that 13 mile, that area at the bottom here, he'll be down here. As he moves back away, his oil line will appear to rise. Now, it's not really rising, it's just an angular size issue. So it will appear to rise and back up, let's just say. So between these two white lines is angular free space. So as he gets closer, that angular free space shrinks, right? As he moves away, the angular free space expands, right? So closer, the angular free space will shrink. As he moves away, the angular free space expands, all right? So if you see it that way. So that angular free space between those two white lines will expand the further he moves away, as in everything he can see within that space will get smaller. So he'll have more things within that space, more view of things within that space. The further he moves back away in a straight line, and the closer he moves to it, he'll have less stuff in that space. So it will begin to tighten up like this, and to shrink. And then as he moves back away, as I said, it will expand again. Now, people like, if anyone out there argues that his oil line may not be at the center here, or he may not be looking exactly, or if there might be the camera slightly tilted, whatever, you can move this down to here. It doesn't matter. It doesn't change the fact. Right? You can see his oil line was there. That's all the same. It won't change anything, because as he moves closer, that'll come down. As he moves away, that'll come back up. Right? That's what happens. It's a natural thing of perspective. So because his oil line, right, as I showed a minute ago, right, his oil line is always making a parallel with the surface of the water or the earth underneath him. So like all observers. So he's looking straight out, and this is the water on earth underneath him, moving straight out underneath. So they're parallel. So this angular free space from orthographic view doesn't change, but from perspective view, looking straight on, what will happen is these two lines will appear to meet, right? That's what will happen, or will appear to get further apart, right? So it will be something like, let me see, go to tools. So I'm just going to annotate this a second. Let's go to line, right? So here is like a yellow line. So as he moves away, that will begin to expand. So these two lines will appear to expand. I just make that slightly more, right? Black, make it a bit thicker. There. So as you can see, this black line here, as he moves away, it will appear, this is the angular free space between the black line and the blue. So it will appear that this space is more, but as he gets closer, it will appear that there's less and less and less and less and less. So that's how it works. But in reality, those two lines never meet. It just appears that way, and that's what ends up creating a horizon. Because a horizon is just a visual thing. It's only an apparent place where the surface of Earth appears to meet the sky, right? So in reality, there's always a parallel between the surface underneath the observer and the oil line, but due to that angular free space expanding and shrinking, it can appear that that there's more or less objects in your shot, let's say, or in your view, than it depends. Depending on if you're closer or further from whatever, something like that, like Barrow. So once again, just like with the black line, this will shrink the closer he gets to it. So he'll end up just looking there, and the further away he gets, the more it will expand. Let's just say that the amount of stuff that's within that, in between those two white lines, right? He'll end up just looking at grains of sand between them, right? If he goes right over to there, but as he moves back, he'll end up seeing more and more and more of the town within that space. Okay, so now I'm going to move on to, just going to show something. This is a comparison that he made himself. This top one is from 1 foot observation height, and this bottom one, I think he said, I'm not sure if it was 30 foot or 50 foot. But as you can see, there's very little difference between them, except for the fact that this one is more horizontal because he's looking straight across the water from a 1 foot observation height. Whereas here, he's looking more down upon all these mounds and stuff over here. I think he said they're like 20 foot in height, these 20 or 30 foot, or maybe he said 30 or 40 foot in height, these sand dunes and stuff over here. He said they're about 30 or 40 foot, I think. He can, if someone asks him, he'll tell him. But over here, as you can see, in the 1 foot observation, they're small, right? They're small because his angle to them is horizontal. Whereas here, he's looking more down upon them because they've changed with it angular. So like that angular free space he has here shows him a different angle than it does up here. So here to here is showing more detail than up here. But he's looking at a more horizontal here. Whereas here, because with the angular size change and his viewer height, he's looking at slightly down upon these, as opposed because he's higher, his viewer height is higher than them. Whereas here he's looking straight over at them. Where is this? I'm just gonna go over here. This is it down here. This area down here, all this area down here. He's looking straight over at it. In the 1 foot observation height, and that's why. Whereas in this one, he's actually higher, so he sees more detail. So he just has like what happens when you go higher, your angle of view changes. You're not looking at something as horizontal. If it's down lower than you, you're looking down towards it. And if you have angular size change happen as well at a distance, then that only makes it easier to see more. So this is a horizontal. This is a slight slope of a view to this mound at the water here. So this is a horizontal from a 1 foot observation height, and this is a slight slope down to the top of this because he's actually slightly higher, I think, than this, and that's after shrinking in angular size too. Now you have angular resolution also, right? Which I'm coming to now in a minute. So now we're going to get to angular resolution. He can't see as much of this from the 1 foot as he can from the 50 foot or 30 foot. Or I think it was 50. It would be 50 foot because he's higher. I think he said it was like 50 foot, and he can't see as much of this at 1 foot than he can higher, let's just say, because of angular resolution. So I'm just going to go down here to this section a second. So I'm just going to go through some stuff here. So angular free space calculations, right? The angular resolution of the human eye is 0.02 degrees. So from a 1 foot observation across 13 miles, which would be 68,000 feet, 68,640 feet, 1 foot of angular free space, which would be the amount, which would be 1 foot across the water from Ranty at 68,640 feet, has an angular size of 0.000083475 degrees. So well below the resolution limit, right? So a 24 foot of angular free space at 68,640 feet is 0.020033 degrees. So from his, I'm just going to show here. So from this position, right, the human eye can only resolve anything that's 24 feet and higher across here at 13 miles away. So anything that's below 24 feet at 13 miles away, the human eye, right, standing here on the beach, can't resolve it, right? You can't resolve that at 13 miles away. So anything below 24 feet you won't resolve correctly. You'll resolve some of it, but bit by bit you won't be able to see it correctly. It'll all just become your horizon. That's basically what happens, right? The diffraction limit kicks in, your resolution kicks in. So that's what I'm talking about here. So something needs to be 24 foot for Ranty from his position on the beach. For Ranty to be able to resolve it with his eye, it needs to be 24 foot in height for him to be able to resolve it at 13 miles away, or 68,640 feet, right? Now, when he's looking across the 18 miles, right, or 95,040 feet, the Barrow Town Hall, which stands at 164 feet tall, 164 foot of angular free space at 95,040 feet is 0.09889 degrees. So he will be able to see the majority of that. he will be able to see the majority of the tower because the tower is so high, 164 feet, like 50 meters. So yeah, he will be able to see it from his. It may not be resolvable here, but his own eye can see the tower across the way there. Now, if I zoom in, it'll be too pixelated, you won't see it. But his own eye will be able to see the tower across the way here, right? But he won't be able to see anything below 20. The tower is 18 miles away, so there'll be even more than 24 foot. You could be talking, I think it's like, could be 30 something foot or something, of the bottom of the tower won't be properly resolvable. Right now, obviously, he has stuff in the way of the bottom, so he won't be able to see it anyway. But the point is that because of the distance, there's a certain amount at the bottom he won't be able to resolve. Okay, so you will have a visual angle of 0.02 degrees, which is the resolution of the human eye, to 6 foot of angular free space at 17,189 feet of distance. Right, so 17,189 feet of distance is 3.255 miles. So what I mean by that there is 6 feet. You will so you're at 3.255 miles away. Anything past that, you won't be able to resolve. The bottom 6 foot of it properly. So at 3.255 miles away is the limit that you will be able to see. The average human eye could be able to see something of 6 foot in height. Okay, so so from looking over the water, the average person won't be able to visually resolve anything smaller than 6 feet in height correctly if it is over 17,189 feet or 3.255 miles away in distance. The average sailboat of about 15 feet in length without sail sits on average about 4 foot over the waterline. So I know this myself as that now I was never in sailboats, was in a lot of fishing boats and a lot of small fishing boats. And after a certain distance, you can't see them. They just become part of the horizon. Because they're only a few feet off a fishing boat or a sailboat is of about 15 foot in length. Is only about 4 foot off over the water. Some of them only 3 foot. So that's a bit of, so what will happen at that distance? So at 3.255 miles away, if something is only 4 foot, you won't be able to resolve it correctly. It will have to be close enough for you to resolve it correctly. So without even bringing in things like inferior mirage and stuff like that, which will block it, you won't be able to resolve it at 3.255 miles away. Okay, so right, so that just shows your resolution limit at 3.255 miles away. Something has to be something has to be about 6 foot for you to be able to see it correctly. And even at that, it's at its maximum. It's at its maximum of resolution. So the next thing I'm going to show is this, right? I've shown this many times and other ones like it. This is my phone, an iPhone 5 I had, and the camera lens on this is 9 millimeters, so 0.325 inches off of the surface of the table. Now it has a 0.0 tilt forward back, so its lens is making a perfect parallel with the surface of the table. Now there is a slight tilt to the right of 0.3, but right to left tilt won't matter. It's the forward and back tilt that matters. Okay, so it's making an absolute parallel. Just as I showed with this. So if you can imagine, this is the camera lens and this is the table underneath it. So the purple line is the camera lens, the blue line is the table underneath it. So the camera lens is making a parallel with the table underneath it. Okay, that's what it's doing. Okay, an optical parallel with a surface. Right, so where's it going to? Right, so so I'm just going to play this on. Right. So as I move this away, right, now it was a bit out of focus when it was so close, but you can see that it's actually slightly higher than the circle here, but that won't matter. That's okay, because as I move it away, it appears to drop, but it's not really. What's happening is this line here, if I just bring it back slightly, right, and back to here, right, there. Right, what you can see is the lines, the black line and the white line, they kind of match up once they're at this distance away. What happens is that this angular size between the angular free space between this black line and the table surface underneath, what happens is as I move away the object, as I move it away, right, what happens is that, right, that begins to shrink, and my white center frame here appears to be able to see more. So it's like the white line here on the surface appears to expand, while that black line there and the surface appears to shrink, because that's going into angular size change. So as it moves away, see? So now it's getting bigger, and the amount of angular free space between the white line and the table has changed, right? Because that's after getting closer, right? So now I can see this from the black line here down to the table, right? But as I move it away, I can see above the black line. Do you understand? So angular free, that's the same here, angular free space as what's between this white line and the table, let's just say. But because once I move it away, due to angular size change, right, it gets smaller, and it appears that I can see more, right? Right, that's all that happens. It appears I can see more, and I'm seeing over it, but I'm not. In reality, that's actually slightly higher than the white. If I bring it in close, it's actually slightly higher, right? So I move it away, it appears to get smaller. As I move it back in, it appears to get, well, it does, it is actually higher. But the point is that that angular free space, right, between that black line and the table shrinks, right? Look at it, it shrinks. Or you could say that the white line, between the white line and the table expands. So as I move that way, that angular free space expands. So you could say it both ways, but as long as you understand the concept of what it is that I'm showing, right? This is important, right? That's what happens, right? So that's 0.325 inches, okay? That's the height of that lens, right? So if I just come back to, here is, yeah, okay. Okay, 9 millimeters or 0.32, 9 millimeters or 0.354, inches of angular free space cannot be correctly resolved past 1012 inches of distance. So what that means is if I could move this back between the black line and the base of the charger there, or the table. If I had a table that was 1020 inches long, I could make the resolution between this black line and the bottom of the charger here. I could make that go into an horizon. That's what that means. Now it gets a bit dark there, so don't worry about that. But if I had enough lighting and enough distance on the table, I could make that shrink, basically be unresolvable at that height of an eye line. Now I know that it's a camera lens, it's not the eye, but I'm talking about the eye height. So at 0.354 inches of eye height above this surface here, I can make that black line, between that black line and the bottom white part of the charger, I can make that whole section appear to be unresolvable at 1012 inches, because that's close on. It's a bit higher. That is a little bit higher than the center camera lens. It is a bit higher than the center camera lens, but I'm just using that as an example. Let's just say it's about the same, right? Either way, I will definitely be making 3/4 of this unresolvable. So it will appear that you won't be at 112 inches. There will be just an horizon line going across there. That's what you will see. You might see the bottom of the circle, black circle, but all this part here won't be resolvable. So it's gone into the diffraction limit. So that's what happens with that, due to angular size change and the change of the angular free space. So so I'll just read this part again. 9 millimeters or 0.354 inches of angular free space cannot be correctly resolved past 1012 inches of distance. Right, 6 feet divides into 3.255 miles, 2,865 times. So 6 foot of angular free space, right, will divide into 3.255 miles 2,685 times. 0.354 inches divides into 1,012 inches 2,859 times, right? There's a small discrepancy between the two, but basically what it shows is is if you treat all them as inches, let's just say, that would mean at 6 inches, basically, at 6 inches, 3.255 was 17,000. So at a distance of 17,189 inches, 6 inches will divide into that 2,865 times, let's just say, right? So 0.354 inches divides into 1,012, 2,859 times, right? Right, but the thing about that is that is the 3.255, or let's just say 17,189 is the resolution limit for that 6 inches, right? So 17,189 inches is the resolution limit for that, for you seeing something of 6 inches high, right? Let's just say, right? If you're looking at about 6 inches high or whatever, that brings it to 0.02 degrees, right? But from a 0.354 inch height, it only takes 1,012 inches for basically almost the same amount of, it's almost divides in about the same amount, but only takes 1,012 inches to get to that 0.02 resolution limit, right? So that proves, right, this proves that the closer your oil line is to the surface, the sooner you meet the 0.02 resolution limit. So this proves the closer you are to a surface, then the sooner the resolution limit happens, right? This is the proof of it, right? There you go. These are the calculations. Anyone can do them, right? Now, I know I'll have a lot of stick from the bowler side about this, but they'll have to just get over it. I don't care what they think. Okay, so it's going to get worse. Not for us, though. So this is Jesse Kozlowski. This is from 2016, if I remember correctly. I argued with him. He brought out 2 videos, so I'm not sure if it's this one or the other one. But the first one he brought out, or whatever, 2016, I told him why this crosshair appears higher than his marker down here. I told him why it was. I told him it was optical drop, like I showed a few minutes ago in this. I told him, this is what it is, Jesse. Now, I didn't have this video at the time, but I knew what it was. I knew it was an angular size change issue. And all it was a change in angular free space, right? I told him this is what it was. And he didn't want to know. It took me 4 days of arguing with the guy before he admitted that he never took angular size change into account. 4 days, 4 days straight of to and fro on YouTube arguing with him. So if we put, give me the second, give me the line. Oh, give me a line, right? There's a line, right? So basically, he's after moving away. If he moves closer, this line is going to come down to here. He'll be right looking straight at it. As he moves away, this line will go back up. It's just a natural thing, angular size change. The further he moves away, the further up that line will go. And the more he'll be able to see up around here. So that's all that was with him. He's a surveyor, and he doesn't seem to understand or want to know that. I don't know what's going on with the guy, but he never wanted to hear about that. And that's 5 years ago. 5 years ago, I was telling him about this. But it doesn't matter. I just said I'd throw that in there because he set it up so his marker over here and his theodolite here are exactly the same height off the surface of the water. So this proves without a doubt what I'm talking about, right? The angular free space. His angular free space has expanded between his oil line here and the water line down there. But as you get closer, it will decrease. Okay, so expand, decrease. Further away, expand, get closer, decrease. Whereas for the marker over here, the closer he gets, the more it expands, right? If this is the marker here and we have the water line down there, the closer he gets, the more it expands, right? But the further away he gets, the more it decreases in size. So the center line, let's say his oil line on here, and the water underneath it, that angular free space will shrink as he moves away, and his own oil line and the water underneath it will appear to expand. And then it's the opposite when he goes closer. So just to show that. Now, I'm just going to show, next is, yes. this. Right, angular free space here, right? This is an observation I made. I was about 70 or 80 feet high, and that's my angular free space. That's my oil line, the center of the camera lens, let's just say, and the surface of the water. That's my angular free space there, right? This is a little lighthouse out here. I'm just going to make this a bit bigger. This is a little lighthouse out here, all right? But I'm actually lower than that lighthouse, which I will show in a minute. But because of angular free space, the angular free space of my oil line on that lighthouse here and the water underneath has shrank, right? Because I'm at such a distance. But when I zoom in, I know it's not the same as getting closer, but it's all I have for the moment. But as I get closer, obviously, no one can argue about it. That lighthouse is going to get bigger, right? So there's my angular free space at the moment. That's the amount I have between my oil line and the horizon, right? So when just going to bring this down, and I'll go back to here, right? Here is where my oil line would be on the lighthouse here, right? That's where my center of my lens is on that. Now it may not be perfect, it might be slightly down more, whatever, but it'll be around about there. And look at my angular free space between my oil line and the horizon now. So it's actually my angular free space has changed between my oil line and the horizon. It's gotten smaller, whereas here it was a lot bigger in comparison to the lighthouse. So the angular free space is kind of the thing. This is not. I'll show you a video now. I'll show you a video that shows the same thing. Angular free space is basically what's shrinking and expanding. So just to show you a video. Where is it? Here we go. Right. Turn off the sound. So as I move, if you can see here, this land here. So I'm looking across, right, from a same location. I'm looking across, and there's some land here, or about same camera height, same location, or a bit slightly to the left of where I was, a bit down a bit, but it's still about same camera height, and looking, it doesn't really matter, just at the same place basically. It's on a cliff, and here you have land. I'm back here, there's water, then this land here, then you have more water, and this island out here. Not sure I think that island is 18 miles away, or 19 miles away, something like that. And my oil line is about here on that. I'm about 74, 70, 75 or something. My oil line is about here on that island. The island is about 100 and something or something feet. So, but when I zoom back a bit, right, watch this island, the top of this island and that piece of land, right? See the way, right? So now I'm technically looking over the island, right? It's like I'm looking directly over the island, and the island here, the angular free space between what looked like the top of the island and the base of the land here has shrank. So let's go back again. They expand, and as I move away, they shrink. But my angular free space angular free space appears to expand. But as you go closer, that expands, and I can see less. But as I move away, that shrinks and I can see more, right? And I'm seeing over the top of it. But when I zoom in, now I have zoomed in, I can zoom in further when I zoom right to the thing, but it does no point because it's a little bit on the blurry side on that day. So as I move away, it shrinks. The distance between this land here and the top of that island shrinks, and I move in, it expands, shrinks, expands, shrinks, expands, and so across a flat plane. And as you can see, I appear to be looking over the top of the island here, right? Whereas when I move in a bit, I'm looking towards where my oil line is on the island. Now, I had my camera on a tripod, it was windy, there might have been some movement around, but it doesn't really matter because the same thing will, what I'm talking about will happen. If you keep a totally steady camera and keep it totally level, that's what will happen as you zoom, because you can't zoom over the top of it because you're not higher than it, right? You can't zoom over the top of it, you're not higher than it. Expand, decrease, okay? Now, that brings us to the last part of this, okay? Okay, the elevation of the sun is the same on any given day from sunrise to sunset, but due to perspective for an observer, it appears to rise and set. So this, right, this is the observer here. The sun here, right, is the same elevation above the ground here. This angular free space between the bottom of what appears to be the bottom of the sun and the ground is exactly the same as over here when the sun was rising, let's just say. So there's the bottom of the sun and the ground. So this is actually the exact elevation, same elevation as here, right? But due to perspective, right, what happens is it appears that the sun is higher at noon than it was early in the morning, right? But it's not true. It's the same, because if I was standing over here at that time in the morning, then that would, or if I was over here where the sun was rising, then the sun would be above my head, right? So it's just so as the sun, let's say it goes from noon, let's say it goes backwards out this way to evening, then it's not that the sun is setting, it's the angular free space between the ground and the sun is shrinking. That's all that's happening. It's just an angular free space thing where the sun, that space is shrinking. Okay, now this is the important one, right? This is a depiction of the sun, right? And as you see, as it goes into the 15 degrees above the horizon point, what happens is that you can see that the sun will start to warp, right? This happens because you're looking at, the angle you're looking at it is through denser air, right? I'm just going to read this, right? The sun's elevation above the Earth's surface never changes, but the angular free space between the surface of the Earth and the sun's apparent position changes in angular size for an observer with distance, giving the impression that the sun is setting, when what's actually happening is the observer's ability to resolve the angular free space between the surface of Earth and the sun's apparent position becomes limited, and eventually the angular free space just becomes the observer's diffraction limit and horizon line, which the sun appears to disappear into. Also, below 15 to 20 degrees over the horizon, the observer is viewing the sun through denser air. So this causes what's known as the sun mirage and gives the impression that the sun is melting into the horizon, as in reality the sun is already out of view and we are just seeing a mirage left behind by it in the 15 degree refractive zone. This would be what's known as the sun mirage, because what happens is that refraction, right? Anyone can Google what the sun mirage is. Just Google sun mirage and look for images, and you see lots of them. It's when you see the sun appearing to be big and melted on the horizon. That's just, the sun is not there anymore. The sun has actually continued moving, but we end up seeing what we think is the sun, and it looks the same size to us when we're looking through the denser air. It looks the same size, but what we're actually doing is seeing a mirage of the sun. The sun itself has moved away, and that angular free space between the ground here and the bottom of the sun, right, has shrank so much that what happens is that as the sun moves away, and the same happens to the mirage, the same thing does happen eventually with the mirage. But if there was no denser air, what we would see is that free space, angular free space there, would just go into zero, and it would become just a horizon. And then bit by bit, as the sun moves away, then what would happen is, I'm just going to get a line here. Line, right. Black, right. And make it a bit smaller, sorry. Right. What would happen is, bit by bit, as the sun, right, moves away, that angular free space would get smaller and smaller between the bottom of the sun and the ground. And then the bottom of the sun would appear to be on that angular free, just basically on the horizon. And as it moves away, and the same what happens with the mirage, eventually it will appear like it's just shrinking into the horizon, but it's not. What's happening is the angular free space it's just the sun has moved away so far, or even just the mirage is after starting to fade. What happens is it just appears to melt down into it, but what's really happening is the sun has moved away out there. That's what's actually happened, because that angular free space has to continually get smaller and smaller and smaller. And so that sun is going to keep on moving this direction, and it's going to keep on, eventually the resolution of that angular free space will just go to zero, and you won't be able to resolve it. And the sun will hit here, and it'll keep on moving, and then you won't be able to resolve. The further it goes, the less you can resolve, and eventually it'll just do that, right? But with the mirage, that's basically what happens anyway, is the mirage eventually moves and melts into the horizon. But what we see in the evening time is not the sun we see the mirage left behind by the sun, especially in the warmer weather. We see the mirage left behind by the sun. Now, I've spoken about this a few times before, and hasn't really caught on. But what people should catch on to in this whole thing is the angular free space and its ability to expand, like over here, right, and decrease. So it expands here. It's all expanded. Loads of space between the bottom of the sun and the ground here. But over here, there seems to be hardly any space, only a small bit. And the further the sun moves away, there's less and less and less of that there is. And that's just a perspective issue. That's all it is. It's just that free space getting smaller and smaller and smaller. And what happens is just becomes you can't resolve what's going on. But in that free space, it's just that becomes just your horizon. So I hope I've made some kind of sense here. It's been a long video. I'm going to stop it now. I might end up making more videos on this, or when I get it down a bit better, I can explain it maybe a bit more succinctly. But hopefully, people who watch this will start understanding what I've been talking about for years and understand what angular free space is. Okay, hopefully you can have your own observations that you can look at it with, and you can do the angular size calculations if you want with the angular size calculator, whatever you want to do. I hope to get some good positive feedback from my own side, the flat earth side. I don't care what the board side think of it, because I know what I'm going to get off them. So I would like some good feedback from my own side and tell me what you think, or what you think I'm right about or wrong about. Thank you. Bye.